All right, and we should be live. Hello, yeah, welcome everyone to this Q&A live stream hosted by Ferrous Systems. In this live stream, I will basically answer any and all questions that you might have regarding contributing to Rust itself or to maybe core parts of the ecosystem, but generally Rust itself, so the compiler and the standard library and the documentation. Yeah, and if there's no questions coming up, then I will basically lay out a couple of contributing workflows that I found to work well and that might save you a lot of time building compilers you don't need when all you want is, for example, just update documentation or change something in the standard library, add a tiny little function. Yeah, so check if coming up. Okay. So first of all, once you've checked out the Rust repo, what you get is something like this, and basically everything you can do here is controlled by the x.py script. And you can already see a little shortcut I've got here. So this is basically a wraparound cargo that will just run whatever cargo subcommand you tell it to, and then either build parts of the standard library, the compiler, or document them, or run all the tests. There's a very extensive test suite for the compiler, most of which you don't need when you don't touch much of the compiler. Second. Okay, this should be better. Yeah, we've got a question by Nick Cernes. What part of Rust could Rust users best contribute to? And well, a common first contribution to Rust itself is usually a tiny typo fix or improvement to the documentation, for example. If you want to do that, for example, the documentation of the standard library is just normal Rust doc, of course, which you can edit by looking in the lib standard source tree here, as you can see here. This is usually very simple. You basically just edit the code, the documentation there. And the way you could, so what many people then want to do is you want to look at your documentation, how it looks when it's actually rendered to HTML. And many people try to do it like this, and this will actually build the compiler not once but twice, I think. So if you pass stage equals 0, then what it will do is it will use the downloaded beta compiler, which is what we use to build the actual Rust compiler. It's always bootstrapped off of the previous release, so whatever is in master is bootstrapped by the current beta release, and beta is bootstrapped by the previous stable release. So if you pass stage 0, it will try to use the downloaded compiler and doesn't actually compile, it doesn't actually build the compiler locally. So if you do this, I've just done that so it finishes instantly, but it will build the build system using the beta compiler, and then it will just run Rust doc on the lib standard. And this basically gives you pretty quick feedback to how your things look. And yeah, then you can, usually the path is somewhere in build. It should be relatively easy to find. Just look for doc and then look into that. It could sometimes happen that this breaks for some reason. For example, when there's new Rust doc features coming up that are only in nightly. In that case, you will need to pass at least stage 1. This will build one compiler, and the Rust doc from the Git version of Rust doc basically, and then you can then will be able to use nightly features. So if I do this, it will actually start to compile LLVM, which is part of the compiler, or what the compiler uses. And this is another neat trick you can do. You don't actually have to wait for it to compile LLVM. You can edit the config.toml, and so whenever you do need to build the compiler, you can usually comment this out, this LLVM config key, and point it to the your local LLVM install. You do have to make sure that you have a version of LLVM installed that Rust actually supports. So currently we support LLVM 9 and 10 and maybe 8. So by default it will build LLVM 9. And yeah, if you pass this, then it will not build the LLVM, which takes a long time, like half an hour or something, depending on your computer. So maybe this doesn't work because my local LLVM might be bad. And I should probably also not build the entire compiler while I'm streaming, so I'm going to just kill this right now. And yeah, this is basically a very simple way to get started by just fixing documentation or improving it. And I'm certain there's still lots of tiny little mistakes that need to be fixed. Another very useful thing that people can do is to just check out the Rust issue tracker here and search for the easy label. And these are issues that Rust maintainers think are very easy to fix for newcomers. These are basically often just renames inside the compiler tree, for example. Those typically might not be trivial, but you don't need to have such a deep understanding of how Rust internally works because you're just renaming things. They can be small, but they can also be fairly large in scope. It really depends. You can basically just check some of these out and see whatever sounds interesting to you. So yeah, that's basically the good introduction issues here. There's also some that are not labeled. You can just, we have over 5,000 open issues. It's kind of hard to keep the labels on them up to date. So there will be many issues that are not that hard to fix, but that are just not marked as easy. So yeah, maybe you can find some other issues too, but there's 2 pages. Some of the issues are also marked as needs test, like here. And those issues, they have been fixed already, but they don't have a test in our test suite. And yeah, this is basically a simple thing to do. Usually you just create a couple of files and then run the test suite to make sure it works. This is another pretty good way to get started because you don't actually need to fix the bug. You just need to make sure the fix actually works. And yeah, other than that, you can also always ask on the Rust Zulip or on the Rust Discord, which is where where much of the compiler team hangs out, and just ask if there's maybe any specific things to help out with. For example, if you are into logic programming and maybe something like Prolog. Rust is currently in the process of migrating some parts of the Rust C type checker to a new trait engine called Chalk, and that basically implements a logic engine. So if you're interested in that, then you can also check out the Chalk working group and ask them for any new issues that they need help with. Yeah, and that's basically a good way to get started here. Of course, we also have some documentation about how to work on the compiler. It's called the Rust C Dev Guide. If you search for that, you should find this. And this basically walks you through different ways to build and run tests for the compiler, and also explains the sort of high-level architecture of the compiler and which parts of the compiler do what and how they interact with each other. So this is very, very helpful. It doesn't document everything, so if you have any questions, just ask on the Zulip or Discord. But it's definitely a very useful resource to get a sort of high-level understanding about how the compiler works, and without going too much in depth, of course. Yeah. Another question by Hamid. How do the different teams in different areas of the compiler communicate? And well, basically the answer there is, I already mentioned this, but we have an official Rust-Lang Discord and also a Zulip instance where much of the compiler work is going on. So yeah, this is, for example, I can show you the Zulip. This is basically just where the where much of the compiler work is can be found. For example, there's different working groups here. The RLS 2.0 working group is the working group working on Rust Analyzer, for example, the new RLS replacement. In tcompiler, you can find general stuff. In tcompiler/help is probably what you want to be looking at when you are just starting out with your contribution. And you basically just open a new topic there, and then pretty likely that someone will help you and answer your question. And yeah, that's also how the compiler contributors or the compiler maintainers themselves communicate, not contribute. But basically, there's also we also sometimes use the Discord, which is sort of unstructured. It's more of an IRC-like chat, basically. But yeah, most of the meetings also happen on Zulip, but there's also video meetings, I believe. And of course, we also have the issue tracker, which is good for more like permanent communication about certain issues or things, which we also use pretty heavily. For example, we open up tracking issues for all RFCs that have been accepted, and so some of these are basically empty threads, but some of the more contentious RFCs have hundreds of comments, because there's just a lot of design work is getting discussed in these issues, because RFCs don't usually specify a feature all the way through, and a lot of things only become apparent. A lot of issues only become apparent when the implementation has actually started. And yeah, this is another venue we use to discuss things. Okay, we have another question by Ferdia. Is it possible for Rust Analyzer to build the compiler and display types syntax highlighting? And the answer is yeah, it should be. At least it's working relatively well for me. You can see this is this right now is in the middle of the compiler, and it's working fine. It does use a lot of memory, so usually it's fine to it's fine with like a couple of gigabytes, but sometimes I did see it using like 7 or 8 gigabytes of RAM, so maybe sometimes you will have issues if you don't have enough there. But yeah, generally it's working pretty well. It even has a configuration where it will run the x.py script that I just showed to actually run cargo check on the compiler, and then you will get inline errors in your editor. So yeah, but the general features are working. Sometimes it takes a while because the compiler is just very large and Rust Analyzer isn't super performant yet, but it's definitely a big improvement over trying to use RLS here, which takes many seconds to get accurate, to actually check things and give you the IDE experience you deserve, I guess. Yeah. Amit is asking, can we as guests join the video meetings as well? And I don't think that's the case, but the video meetings do get recorded and they get uploaded to the official Rust-Lang YouTube account, I think. So you can check out old meetings there and yeah, basically figure out what the team has been talking about there. I think this is mostly something the language team is doing to discuss language design questions, while other teams might use other venues to discuss things. So if you're interested in the language design aspect of things, then the YouTube account is probably a a good thing to look at. Yeah, people are saying that could not use Rust Analyzer and VS Code until they changed to an SSD and 12 gigabytes of RAM from 8. And yeah, that basically mirrors my experience as well. I would recommend at least having 16 gigabytes of RAM if you want to contribute to the compiler, especially because Rust Analyzer uses a lot of memory, and when you then start building the compiler, that quickly makes you run out of memory. They're asking, how do you manage to run x.py for cargo check in VS Code? I'm not sure if I have this set up right here. But basically there's you need to open the settings of Rust Analyzer and tell it to and change the default command it will run. Instead of cargo check, to use x.py check. This is probably also documented somewhere. It's a really recent feature. I think it has only been in Rust Analyzer for a couple of weeks now. And yeah, I don't think I have it enabled here. Oh, it's trying to run cargo check. And sometimes this even works, but it won't work on the entire compiler, I believe. Yeah, okay, this might take a while because I haven't built the compiler before, after I just updated the repo. Yeah, okay, seems like it doesn't work right here, but it's trying. So yeah, I'm not entirely sure where the configuration for that is stored. Okay. Looks like Alexei has posted the configuration you need in the chat. So yeah, Alexei is my coworker, and he's kind of assisting me with this stream. And he also implemented the feature we are talking about. So yeah. Kevin is asking, how long does your cargo check usually run? And for fresh checkout, usually checking the entire compiler tree takes a couple of minutes. But once you've done that once, it usually isn't too bad. So some of the bigger compiler crates do take a couple of seconds to check completely. So this, what you just saw, took a long time because I haven't built the compiler from this source tree after updating it. So it had to actually compile all the compiler dependencies. and basically run through all of that. So it took a long while, comparatively at least. But this is only the first time. So now if I do some other changes, you can see, yeah, cargo check is finished, but of course it's not the right command. So I think we get, yeah, a lot of errors because it's running the wrong command here. So yeah, and usually once you've got that set up, then actually working on the compiler is surprisingly painless until you need to actually build it and run the entire test suite. Then that can take a while. So usually I wouldn't say it's terribly painful nowadays because there's actually been quite a lot of work to split up the compiler in more manageable chunks. So we used to have one crate in there that was just called librustc that contained basically most of the compiler, and that has been split out and thinned out into many more smaller crates. So now building the compiler is not actually that bad. It's still not instant, of course, but I don't think you can really expect that for a language like Rust, building a project as big as Rust-C. But usually it's not that painful, especially if you enable incremental compilation. That's another, it's off by default for some reason. I think there's still some issues to be worked out there, but if you turn on the incremental key in your config.toml, then it will actually do incremental builds, and if you have to change only a small part of a compiler crate that takes a long time to build, then it will only rebuild what it needs. And well, I should probably turn that back off, because then it would rebuild the entire compiler again when I do this. But yeah, this also helps a lot if you need to actually interactively change the compiler and want quick feedback. So this is a very useful option to turn on. So yeah, I should probably start writing this down. So yeah, like I said, if you really only change documentation, you can look at them without building the entire compiler. And if you only change lib standard, then you can just run cargo check on the standard library, essentially by doing this. Of course, often you want to modify data structure, for example, and for that you should be able to use x.pytest and also with the stage 0 flag without actually building the compiler. But these stage 0 options, they can break from time to time because of unstable features being used in the standard library or the compiler. And then you unfortunately do have to build the compiler. And there's other tricks you could use documented in the Rust-C development guide that I just mentioned. And yeah, it looks like this is working. Sometimes you can even use cargo test directly for running tests, for example, on an internal compiler crate. And as soon as it doesn't have dependencies that are too complicated and actually need support from the build system, that also works just fine. So if there's basically if there's some change needed to a compiler data structure, they are in their own crate, and you can just run all the tests there with a cargo invocation, and that's pretty useful. Yeah, so the lib standard tests are running fine. Yeah, what you do is you can just call cargo test and then pass the package name, which is in this case Rust C data structures, which just contains a bunch of data structures used in the compiler. And this will just basically do what you expect. And it doesn't work on every crate, but it works on the most important ones, I think. And yeah, makes things just much easier than sitting through an entire compiler build. So yeah. Yeah, let me also write down where to find issues to contribute to. So yeah, like I said, you can check the issue tracker for labels easy and needs test. You can also ask the compiler team or working groups. Yeah, there's also the C cleanup category. Okay, I have too many labels applied now. So C cleanup is usually things that just should be done, but they have no visible impact on how the compiler works or which programs are accepted. So they usually don't need much politics. Basically, you don't really need to wait for for the team to approve it. It's enough if just someone from the compiler team reviews your PR and accepts it. And the nice thing about the C cleanup issues is that they, at least for me, personally, I really enjoy this sort of refactoring work because Rust really guides you towards what you need to do. So yeah, depending on what you like to work on, of course, I usually find these to be relatively pleasant, I guess. And yeah, these are, I think, basically all of those are in the compiler itself. So they aren't necessarily easy because they are still there's still like active discussion needed to figure out how to do it well. But generally, a lot of these are relatively easy to fix. And yeah, I guess you would have to check them yourself and maybe ask if there's been any updates on that, and maybe for guidance by some other team member. But usually these are pretty good way to basically get deeper into the weeds of the compiler. I should probably add to this, when you do want to do something on the entire compiler that requires integration tests, then you don't want to do x.py test, because this will again build it will build the compiler and then it will use that compiler to build the compiler again, which is a nice, basically a sanity check that the build system is doing, but it just takes a long time to do. So usually what I do, but no, not usually, always what I do is, unless I don't need my computer, I do test stage with stage 1. This will use the downloaded compiler to build the compiler once and then test that build compiler. And this is usually all you need to evaluate if any contribution to the compiler, basically. It will run the entire test suite and also the tidy checks that are run on CI, which check things like that you don't have more than 100 characters per line and that everything is formatted and that files are not longer than, I think, 5,000 lines. So these are always pretty trivial things the pull request can fail on. So just running the test beforehand is actually something you can also do explicitly. And for that, let me check. I think you need, yeah, you would run stage 0 or 1, doesn't really matter here, I think. Source tools tidy. This will first build the tidy tool, and then just run that on your source tree and check that just general code style things are enforced. So yeah, this is definitely a useful thing to do before opening a PR and then seeing it fail within seconds because some line is too long or something. That's always, it's always good if you can rule that out before doing it, even though it doesn't really matter. If it fails, you just fix it and push another commit. But yeah, it's usually nice if I open a pull request on the compiler and run the entire stage 1 test suite, then I'm always fairly certain that it's actually it would actually pass and can be merged relatively quickly. Should probably stop this. Yeah. Panstromek is asking, compiler performance has been a hot topic lately. What would be a good way to get involved in efforts to speed up the compiler? There's a working group for compiler performance. You can either ask them, you can also, if you think you can commit regular time to it, or if you think it makes sense to join that working group, that's also a thing you can do. But generally you don't need to. It's totally fine if you just work on your own, just do performance work and then open PRs. But you can definitely coordinate with the working group to see if they have, if you have, for example, an example that compiles slower than you think it should, then you can ask them if they have any idea. It's also fine if you have a small example that you can use to reproduce the issue, that you can just open an issue in the issue tracker, because normally we do consider untypically long compile times a bug, but of course nobody is really expecting Rust to compile as fast as Go because the language was just not designed in that way. So, but if it's really untypical, then of course it's fine to open an issue for that. And yeah, maybe I can list a few things that I tend to do. I haven't really found something that really works terribly reliably for investigating compiler, for profiling compiler, for example. But there's a couple of things you can try out. someone's mentioning mere optimizations, which have definitely helped in the past with compiler performance. And I can go into some detail on that later. I just list some tooling that I sometimes use. Basically, I'm just trying out things and see what sticks, because benchmarking the compiler is not terribly easy. We do have a self-profiler built in, which you can, it's also listed in the Rust C dev guide. So if you run the compiler with the self-profile, it will actually collect internal statistics on how long certain queries inside the compiler are taking. For example, type checking the body of a certain function is a query, and it will record that time. And if you, I think there's more options to this. I'm not entirely sure how to control all of it, but it should be documented in the Rust C dev guide. You can actually use this to generate a profile that will then tell you which function takes how many milliseconds to type check, which is pretty nice actually. And yeah, if you see something that's out of the ordinary there, then it's also very, very helpful if you open an issue and include that. Generally, if we can narrow it down to a single function that just takes a surprising amount of time to type check or to borrow check, maybe the borrow check has also had some performance issues in the past, then that's always very, very helpful for us to find the cause and fix it later, and also for having a test case that we can then add to the performance tracker. Maybe I show that right now. So on perf.rustlang.org you can we actually track the compiler performance, and you can see that you can see all kinds of benchmarks we have here, and how long they take to compile, or rather how many instructions the compiler needs to compile them, which is just a more stable metric, but it's basically strongly related to the time the compiler needs to compile them. So yeah, you can see a couple of spikes when we regress something and then fix it again. And generally these tend to go down, maybe not always, but mostly. So yeah, this is also something you can run on individual pull requests to figure out if they actually improve performance. But generally, once you've figured out maybe parts of the compiler that take long and maybe collected a profile using perf or flame graph, then you can already see a couple of individual functions inside the compiler code base that take a long time to run. And then if you just look at them, you might be able to see something to improve already. Yeah, usually there's quite a few low-hanging fruits still in the compiler that anyone can just basically pick if they want. We just need to know where they are, because the compiler is so huge it's sometimes not entirely obvious, and that's where these tools come in. Yeah, it's just kind of hard to see where one can help with limited time. That's definitely true. I think what you can also help out with is there's a couple of course we also track compile time issues here in the bug tracker using this label. And a lot of these are marked as needs MCVE, which means that we don't really have a small example that reproduces the issue. And if you want, and if you feel like this is something you enjoy doing, then it's definitely very helpful if we can get this sort of example, and because that just makes it way easier to turn that into a test later and to run the compiler on that example. So you don't have to build, for example, an entire web framework with hundreds of dependencies just to see the problem in the end. So this is definitely something that helps. I don't think all of them are labeled completely correctly. But yeah, this is something that you can definitely help out with if you only have limited amount of time. Yeah, and if there's anything else you want to know, then you can also ask the compiler performance working group, or just generally the compiler team Zulip. There's usually people that can help you with things there. Yeah, so generally working in the compiler always feels like there's this huge thing that I don't really know what it does in all the places, and that's also still the case for me. I don't really understand how parts of the mere borrow checker works, or lifetime inference, or parts of the type and trade system, especially around higher ranked trade bounds. But because the compiler is so big, it also means that there are bound to be a huge amount of things in it that are very simple to understand and to figure out, basically. Mm-hmm. Yeah, that's cool. Okay, yeah. They made the performance tracking page load faster, which is also useful performance work. Not on the compiler itself, but it's still helpful to work on this page. Yeah. This is actually a really nice thing to have because we can see performance impact of all pull requests as they are landed, and also track them over time. And this is really, really valuable if we want to be serious about optimizing compiler performance. So any work done on this is also helping other people maybe work on the compiler more effectively, because they have an easier time seeing this or like using this data that we collect here. Yeah. So people have been talking about mere optimizations too. It's actually people that have worked on constant propagation, looks like. So there's a couple of, I think, noteworthy optimization passes. We already have a couple of simple optimization passes that just eliminate redundant blocks and combine certain statements, so to just remove code that is very clearly useless. Wait. Actually, so first I should maybe explain what MIA actually is. MIA is basically just one of the compiler's internal representations for Rust code. And basically we pass the compiler, we pass the source code, turn it into an abstract syntax tree, which is basically very, very close to the input source. Then we turn that into the high-level intermediate representation, or HIR, which is basically also in AST, but with many things removed. For example, there's no if, I think. Instead, everything's just match. There's also no if let. This is also just match. And then we turn that into MIA. And MIA is very different from the other representations, because this is actually much simplified. For example, things like auto deref, they are all explicit in MIA. And this means that it's much easier to implement compiler backends. So the CodeGen backend uses MIA and turns that into LVMIR. And also the interpreter Miri, which is used for evaluating constants, is using Mir because it's just way simpler compared to the full semantics in Rust code. So basically this is the compiler pipeline simplified a bit. And the Mir representation is actually simple enough that we can do optimizations directly on it. And it's also in a control flow graph form, which means that you don't have a tree that resembles how the source code looks, but it's instead sort of just blocks that jump to other blocks. And this is basically exactly the sort of thing that a compiler needs, that a compiler wants, and that optimizations that are established want. It's not quite the best form you could use for doing optimizations on it, because it's not in SSA form, which is a static single assignment. It's basically just something that makes it much easier to write optimization passes. LVMIR is in this form. So and LVM is still and will always do the bulk of the optimization work. But where Mir optimizations really shine is when they can remove much redundant code, or when they can do things that LVM is bad at. And this is something we are exploring currently. We do have a few very simple passes, like the inst combine and the simplify CFG pass. Those are basically, they just look at patterns in the Mir and replace them by simpler patterns. We have lots of simplify X passes that just handle a very specific pattern. Then there's more noteworthy optimizations that are run by default, is, for example, const prop, constant propagation. And this basically calculates the value of constant expressions in the in the Rust code before handing that to LLVM, which is useful because the value that will result is always the same, and then LLVM doesn't have to do that work. And we also save the work of actually translating the Mir to LLVM-IR. So and one of the reasons why optimizations on Mir can have more impact than on LLVM-IR, and they can also positively impact compile times, is that Mir is always in a generic form. So if you have a function that's generic, once it's at this level, generic types are always replaced with the concrete type through monomorphization. Just like in C++, templates are basically or template parameters are substituted with concrete types and values. But in Mir, this is not the case. Mir is completely generic. And that means if we can do optimizations on Mir before going down to this level, we actually save the work LLVM would otherwise do, but times n potentially. So for each instantiation of the Mir function, we save the work. We just do it once here instead of n times on LLVM's level here. So this makes optimizations there very powerful, because they can just save the work multiple times on that LLVM would otherwise do. So constant propagation is basically using the constant evaluation mechanism, Miri, to just opportunistically look at source code that can be evaluated like this, and then just writes the result in wherever it would be stored. This is very useful. It has, I think, improved compile times all across the board by, I'm not sure about the numbers, but 10-20% or something maybe. We also have other passes that, this is the folder you want to look at if you're interested in this sort of stuff. It's in librustcmir transform. Now this doesn't only contain optimizations, but also passes like the generator transform, which powers async await. And this is also something that's very, where this representation Mir is useful for, because this transformation is not that complicated. But it's not an optimization, it's just something that needs to be done for every async function you write. Other optimization passes that are useful or that are currently being worked on is the inliner. So inlining is something that Rust is doing very, very heavily and relies on for a lot of performance and a lot of the abstractions. It's all done by LLVM at the moment. Okay, constant propagation. Someone says constant propagation is not using Miri, but I believe it is still using the underlying const eval engine. So Miri is the external tool that you can use to check Rust code for unsound operations. And it also hooks into the same underlying constant evaluation engine in the Rust compiler to do that. It's just interpreting all Rust code at runtime. And yeah, constant propagation is built on the same sort of groundwork used for evaluating constants. So yeah, the inliner is another optimization pass that can potentially be a big bonus because, again, we can do the inlining on Mir if we know the call target. So if there's no generics involved in the call, then we can inline the Mir before actually going down to LVMIR, and instead of creating all the trivial functions that we would call, we just inline them here and create the original function once and lower that to LVMIR. And yeah, this is something that has been in the compiler for quite a while, but it has, I think it might still have some bugs, but people are definitely actively working on making the inliner usable by default. And yeah, the goal is to, I wouldn't be surprised if we would turn this on by default in the coming months at least. So this is definitely something that people are actively looking into. I've personally also experimented with copy propagation, or rather NRVO, which is named return value optimization from C++. Mir contains a lot of redundant moves of data, so you have statements like 1 equals 0, or no, 1 equals 2 maybe, and then this is redundant, of course, because you could just move the value in 2 to variable 3 right away. And this is something that constant propagation and NRVO can help with. There's basically different approaches to doing this, and we have actually had a copy propagation pass for a long time now, which is in copy prop here. So yeah, you can check that out if you want. But I don't think this is going to be turned on by default because it still has issues, and it also doesn't handle. It is also very slow, and it doesn't handle a lot of cases that would be useful to handle. And that's where some of the experimentation we did around NRVO come in. And yeah, I did open a PR with a very simple version of NRVO, but eventually had to close it because it was just the approach would just be way too slow, and I wanted to wait until we had the proper analysis in place that would make this easier. So there's definitely multiple people interested in this, so there's probably going to be some work on this in the future. And yeah, if you are interested in this sort of stuff, it's basically, it has been a lot of fun to work on this, even though the PR was closed because it was just too slow. But I'm definitely keeping track of who's working on that and maybe helping out in the future. Okay. Yeah, so basically this is the gist of the current Mir optimizations and why they are useful, and where we are trying to go. Most of these are also on by default. There has been some work on simplifying try expressions, or like the question mark operator, basically. Which turns out it's not always actually zero cost to use the question mark operator because LLVM is having some trouble with the redundant moves it creates, and the simplification. Some of the simplify passes here, for example, simplify try, is to simplify these matches that are generated by the question mark operator to something simpler. And yeah, that's also something people have been working on a couple of months ago, I think. But because the question mark operator uses into, it will actually lower to a function call, and the function call doesn't get inlined until the inliner is turned on by default. So this is definitely a useful thing to do to unlock future optimizations here. Yeah, so I'm not personally involved in the inliner, but I know other people are. And this stuff is still work in progress. Or rather, for NRVO, some data flow analysis work needs to be done. I think it's actually almost there now. So we could reinvestigate that in the near future. So yeah, it's always cool to see so much progress being made in such a short time, because it was just a couple of weeks ago where I actually worked on this. Yeah, but basically this is the gist of what these passes are trying to do, or at least some of them, not all of them. Some of them are also checks for that will just emit compiler errors when something is wrong, or just things that need to run all the time and not necessarily are not optimizations. Yeah. Oh, and one thing is you can also just look at the mir generated by any Rust program by just going to the playground and choosing this mir button here. So yeah, this is basically how this representation internally looks. Yeah, as you can see, there's lots of assignments. And yeah, most of them are basically redundant, or like not most of them, but many of them are tend to be redundant here, because it's just easier to reason about whether doing it redundantly would be correct, while trying to avoid that in the beginning might not be correct in all cases. So it's easier to basically start by emitting more inefficient code and then leaving it to optimizations, which remove them if possible. And most of the time, LLVM is actually doing a pretty good job at this. So it does, of course, have some capacity to remove redundant copies. But it's just not always good at this. So for these remaining cases, it's really where the mir optimizations could actually improve the runtime of the program a lot. Copy propagation in particular is not likely to improve compile times, but it definitely has the chance to make a lot of patterns much cheaper than they are currently. So for example, whenever you have sort of large structs and you have a function that returns one, and you do something like this. You create the struct, then you manipulate something, and then you return the struct. This will probably end up doing a redundant copy from this local variable to the return place, which is the return place in mir is always _0 here. So that's basically just, yeah, in this case it's, wait. Yeah, you can see here, local 0 is of type buff, and before returning it will assign the returned value to this variable. And, oh, this is actually the constructor here. This is function f. Yeah, you can see we have two variables of type buff. And yeah, we start by initializing variable 2 with the array and then moving that into variable 1. And then we index that and set the index 9 to value of 1, 2, 3. Then we move the entire value to local 0 and return that. So this is something that can potentially be addressed by an RVO. This is the sort of pattern it can optimize. And LLVM is not terribly good at this. It is usually helpful with other sorts of redundant moves, but this specific pattern is something that LLVM doesn't necessarily cover very well. Unless it inlines everything and just basically reduces the code down to nothing. But you do have to get somewhat lucky for that to happen, basically. So yeah, it's cool. It's actually some people watching the stream that are doing some work themselves on the compiler, the copy propagation, the constant propagation path, and also the performance test suite, which is always really useful to see. It's really cool. So yeah, if you're interested in this sort of stuff, then there's always some work on the, of course, also a working group that is doing specifically MIR optimizations called Working Group MIR-opt. And yeah, if you are interested in this sort of stuff, then feel free to contact these folks on Zulip, and they will probably be able to explain things to you and maybe even find something to work on. Or generally, maybe just check out the code in the transform folder, the modules here. This is generally something I do quite a lot when I'm not entirely sure how something works. I just dive into the code somewhere and try to follow it along, and that usually I might not understand everything, but at least I go away knowing more than I did before, or maybe at least having some deeper insights into how things work, like the generator transform. You might have seen the work I did to allow async await on no-stood and embedded targets. Before that, I didn't really understand. I understood the general concept of how async await was compiled, but I have never actually contributed to this or understood really what's going on here. And this is all something I just learned by staring at the code for long enough. And usually that's a good approach when you're somewhat intermediate. So you have some idea about how things work, but you're not entirely sure. At that point, it can be useful to maybe just take a deep breath and just dive in, because usually it will either end up with you implementing something really cool, or maybe with you finding some inefficiency and improving that and making the compiler faster, because those are sometimes relatively easy to spot even. And even if not, you will at least go away from that knowing more about what's going on, right? Yeah. Okay, I think I'm going to, it's been an hour now. I think I'm going to take a quick break, and think I will be back in maybe like 10 minutes. Okay. Okay, and we are back. Yeah. Okay, yeah. You might have seen this in the chat already. This is part of our Rust Experts offer, basically. That's an offer that you can use to get all of us at Ferrous to answer your questions. We offer that for companies and also for individuals. So, and we currently have a special offer for 64 euros for 2 weeks that you can try it out. So if this is something you think could be useful for you or your company, then please check that out. Yeah, we can basically help you with all kinds of questions around the ecosystem or your application, how to structure things, and yeah, anything like that, basically. Okay, one thing I forgot to mention is actually that the built-in self-profiling functionality it also has a working group called Working Group Self-Profile, I believe. And yeah, this is actually something that that's already pretty useful, but it can still be improved a lot. So if you think that you don't really that doing the performance optimizations directly isn't really something you are interested in, but then maybe checking out the self-profiling code is something that you might want to work on, because it enables people to much more quickly find which parts of the compiler are actually slow. And currently this is a bit hard to use. You first have to run the compiler, and then it will spit out a profile or merge profiles from multiple runs. And then you need to use an external tool, which you first have to build in order to turn this into data you can actually use. You can either you can either just list it as a table in your command line, or you can turn it into profiling data that can be read by Chromium, which is pretty neat. But it's all external tools, and it's not exactly easy to use. So there's definitely something that can be improved here. Which is also some. This is also a support role. Basically, it's not directly doing the performance improvements, but it's definitely helping the people that do work on that. So this is definitely helpful. Yeah, check out this working group on Zulip if you are interested in that. Oh yeah, and of course we also publish the compiler the documentation of the internal compiler crates. So this is Rust C middle. So yeah, we basically generate documentation. We generate and host documentation for all the Rust C crates. Yeah, you can basically check them out here. They all have some level of documentation, and the Rust C dev guide also basically tells you which crate is for what, and yeah, and this is very helpful because it tells you about the API you can use. For example, the mir data definitions are in the Rust C middle mir. And yeah, this looks like a lot of stuff, but most of it is things you don't really deal with a lot. So this is still a relatively simple representation. So like you saw here, every function gets turned into a list of blocks, bb1, bb2, and things like that, and each block contains a bunch of statements, which can then jump to other blocks. And that's represented here as the so first you have the body, which is can be a function or constant or something that can be basically evaluated or called. And yeah, this has a bunch of local declarations in it, a bunch of other stuff that is only used by, for example, mere borrow check that we don't really have to deal with. So a lot of this stuff can just be ignored because it's just very specific and not usually something you need to worry about. And then all the blocks get put in this list here. So each block is just a list of statements. Can be very long, or they can have no statements at all. And then they will always have a terminator. Even though it's an option, it's only none while the mir is being built. Once the optimizations actually get to deal with this, the terminator is always filled in. The terminator can be something like a function call or just a goto. So yeah, Rust actually does have goto in this representation, but it's not exposed in syntax, of course. So yeah, for example, here is a call to the fmt arguments new v1 function. This is just something that the println here expands to. So yeah, that's basically the representation that all the mir passes are built on top of. Someone's asking, copy prop should always be used before const prop, right? That's actually a good question. Let's check what's the case right now, because copy prop is not run by default. So right now we have const prop runs here and copy prop runs a bit later. So what I'm thinking is that since copy propagation, all that will do is replace these sorts of statements when they aren't needed, and deleting those statements. It might not actually matter if const prop knows that the value is a constant here. It will propagate it into this value, I think. And then if it's still then it still knows that it's a constant at this point. But maybe there's a limitation in it that makes it not do that. But at least this is my model of how constant propagation works. One of the issues with this is that if you propagate code, if you propagate constants, then you might end up messing with the debug info, which is actually kind of important not to do. So maybe constant propagation is deliberately limited to certain constructs where that's not an issue. And I know that copy propagation definitely messes with debug info in a way that it shouldn't right now. Yeah, and we do also have a pass that will, for example, clean up locals that aren't used. So if you run copy propagation, it will delete this statement and replace, for example, one thing that my NRVO pass would actually do here is delete this and replace this 10 with the _5 here directly. And if that happens, then we do have another pass that will notice that the local 10 here is not actually used and will delete it here. I think it's called simplified locals. Yeah, this one here. This is actually probably a relatively simple pass, so it's good if you are looking if you want to check out how a simple mir pass looks. This is probably a good candidate. So yeah, there's actually lots of simplification passes in this file. Most of them are relatively straightforward, I believe. Yeah, this is the mod file in the transform folder is also very useful to look at if you want to see what actually runs when, because this actually contains I think this is a bunch of stuff that is not for optimizations, but it will basically remove annotations and things that are only needed by mere borrow check, which also runs on the mere representation, of course, and then do things that are independent of actually optimizing stuff. The add retag, I think, is needed for Miri, or maybe it's something experimental. And then there's the actual optimizations. And currently, I don't think we... so there's a nightly compiler flag called the mere opt level, which you can use to actually run more passes like copyprop. Yeah, copy propagation is gated on mere opt level 2, I think. Everything else runs at mere opt level 1, which is actually the default, even if you don't tell rustc to optimize at all. So they actually will run by default, which makes sense because things like constant propagation will speed up the compiler and improve compile time. So it's useful to do that even for debug builds. And yeah, definitely, I definitely expect that at least by the point we have better copy propagation in the compiler, we will have passes that will run based on the opt level, so that we don't run the expensive NRVO pass for debug builds, but only for release builds. Yeah. I think the debug info stuff only matters for debug builds. Yeah, that's true. Yeah, when the compiler gets the debug info, like when the user requests debug info to be generated, which is the default for debug builds, only then we actually have to care about debug info. I don't think we currently have any logic for that in the passes. But yeah, an issue is that Rust is relatively bad at emitting debug info. At least some of that is caused by LLVM eliminating that during optimization or not having good support for debug info in some cases. But yeah, it's definitely something that technically you don't need to care about debug info at all when you are not emitting any, of course. But it's if you do, then it would always be useful if the pass actually handled debug info correctly and doesn't mangle it in any way. Because then you have the chance to actually run the optimization pass in debug builds and speed up the compiler with them. So another relatively simple pass here is release. Yeah. Oh no, there's another one I was thinking about. I think it's just simplify CFG is doing some of that. Yeah, collapse go-to chain is basically the logic that will take a block that jumps to a block that is empty except a go-to terminator at the end, and then just collapse that chain so it directly jumps into the target block. It's also relatively simple logic here, and we do actually end up generating this code after some other optimizations, I believe, or some other transformations are running. So yeah, this is just a small simplification of the control flow. And it's relatively easy to understand the logic there. And that also shows why this the mere representation is actually pretty useful for these optimizations, because all of the control flow is explicit in mir, and you can directly see where code goes after it finishes executing. And that's not exactly the case for the high-level IR or the AST, which are all just resemble the source code. And yeah, that's basically where the power of mir comes in. And like I said, the fact that it's generic and pre-monomorphization makes optimizations here basically take effect many times if the function is used with different generic arguments a lot of times. Yeah, Panstromek is saying there were some other ideas about optimizing generics to not emit too many monomorphizations. And yeah, that's something that that David Too's polymorphization pull request is working on. Yeah, that's basically the result of their master's thesis, I believe. So basically, the issue that that's solving is when you have a generic function and then you create a closure inside of it by doing, I don't know. Closures are very often and for example, if you have this sort of construct here with the closure here, the closure actually inherits the generics of the containing function, so the t here, even if the closure is not affected by the generic at all. So if you call f 10 times with different types here, we would also end up creating 10 different closures, at least on the LLVM level. And that's what this polymorphization work is basically trying to eliminate, among other stuff. I think it also will handle this generically, so if you just accept a type that never actually matters in the function body, then you can call this with any amount of any different types you want without actually having multiple instances generated in LLVM code. So yeah, that's definitely something pretty neat, and I'm also I'm excited to see that land. Not sure what the status of that is, but I definitely saw the pull request being opened. And yeah, I expect this might also reduce compile times by quite a lot by reducing code like this with lots of closures in it, and not doing that as much redundant work, which does come up in certain code bases a lot. Not in all of them, but there's basically, it's very rare that an optimization actually applies all across the board like that. So yeah, but I definitely think this is going to be very, very helpful for compiler performance. And with no effect in runtime performance, of course, because we would just hand LLVM the same code twice, and it will probably end up merging the functions together anyways, which is something LLVM can do. And yeah, it's basically just something that will improve compile times and without any drawbacks. At least that's what I understand. I haven't looked into it too deeply, but yeah, that's my understanding. I also had, actually no, I was thinking about some ideas that go beyond that. One pattern that you might see is something like this, where you have a generic function that is that can take any implementer of into, or another common case is as ref, but then it will just do it will end up doing something like this, and then working with the X type in the rest of the function, like, I don't know. You might have something like this. This might be any sort of more complex operation. And people have definitely noticed that this would create a new instance of this function for every type you call it with, even though most of it is just the same. So a common pattern that someone has even written a macro for that does it automatically for you is to just basically wrap this to basically replace the part of the function that is not dependent on any generics to outline that into a different function that will then do the actual work but is not generic. So in this case, you would end up having this function once, regardless of how many times this is called. And if you call this with multiple different types for x, you would just end up monomorphizing this small part, which is just two function calls and maybe a bunch of copies of the local, it would just monomorphize this multiple times. And that's much more efficient than monomorphizing the entire thing here multiple times. So this might be not just a print, but a much more complicated computation. And I was actually thinking about making a sort of outlining path that does this automatically for you, built on the polymorphization work. But that's basically just an idea I have right now. I don't really know. I don't really know how difficult it would be to implement this. But it's definitely something that that is a real possibility, because we have seen that it does affect real world code, right? So people have noticed this pretty early on. And there's like I said, there's a macro. I think it's called Momo that you can put on a function to do this automatically. So there's definitely something to be gained from implementing this in the compiler in a transparent way, that you don't have to worry about this. But yeah, I don't really know how big the impact would be though. So it might just turn out that this is only in very specific cases something that you need to worry about. And then even then people already do that by hand. So maybe it's not that big of an impact, but it's kind of hard to evaluate without trying it out. And I think it could actually be pretty fun to implement. Maybe once the polymorphization work is done, which might help with this, maybe. And yeah, this is just one of the ideas. Like I said, there's plenty of ideas to be had still regarding the optimizations. Some things we know we want, and some things maybe we haven't even figured out how to do yet. And there's definitely a lot of room where people can help. Not with code, but also just with having the right idea basically at the right time. Okay. Maybe one thing that might be useful for people looking to contribute is to check out how the compiler test suite actually works. So the tests are all in source /test. And so we do actually also have tests for mere optimizations. They basically the compiler has the ability to output the mir not just once for the compilation, but also before and after any given mir pass runs. So yeah, for example, we have some of the simplify passes. Actually, we have some of the copy propagation tests here that will basically just run on some simple Rust code. Here, of course, is a pretty clear case where the copy from X to Y can be omitted. So this will emit the difference between before and after this copy propagation pass into this file. So this will end up in copy prop, I think. No, in copy propagation.diff, yeah. And basically, yeah, you can see it does do its job here. And basically just turns the entire body of the function into one that just copies the argument to the return place and then returns. So yeah, that does seem to be working. And yeah, basically we have similar tests like this for a whole bunch of these mere passes and the mere transformations and optimizations. There's also some of the generator tests that at any point, this is one I wrote. Basically, I added an optimization for generators to not generate so many panicking branches when, for example, panic abort is set. And this is the test that came out in the end. And I think what this is checking, yeah. Basically, this will only contain, this does not contain a single assert statement. Yeah. I'm not going to go into much detail about the generator transform because that's a whole nother thing. Yeah, but basically this is how mere optimizations and passes are tested. And all the other compiler tests are, or most of the interesting compiler tests outside of mere optimization tests are in the UI folder. This basically, this is the async await test suite. These tests are basically, they have these commands at the top, which tell the test runner what kind of test it is. And this is all documented in the, so most of this is also documented in the Rust CDev guide, so maybe check that out for a better reference than me talking about this right now. This is one that is expected to run and exit successfully. So when the compiler emits an error here, the test would fail, and and also when this program gets compiled and executed and the assertion would fail, the test would also fail. Or when the program would crash, for example, which is something that also sometimes happens. There's a whole bunch of tests. Just the UI tests alone are almost 10,000 of them. So yeah, I have no idea what most of these do. Don't get scared by the numbers. Just look at what seems to be the folder you're looking for and put your test in there, and then you're basically good. There's also a bunch of other test suites that are more complicated. The run make test suites, for example. Here's where the embedded targets get tested. The run make test suites work by just simply executing make on a make file and checking the return value. This will only execute when the target we are building for is one of the ARM thumb targets. And this will then run this script, and it will actually build the target and run it in QEMU, and then check for the expected output here, which is x equals 42. This is basically just a very, very simple sanity check where the code here will print a number using semi-hosting, and then we just check for that in the QEMU output. And so this is basically how you could do more complicated tests that don't just check the compiler output. This is basically the most important test suites, I believe. It's also debug info tests. Those actually run a script through the GDB debugger. And then check the output of that. I haven't really had to deal with these because debug info is something I haven't worked with. I just know these tests exist, and so if you would if these start failing because of a mere optimization, for example, then maybe the me optimization hasn't properly handled the debug info, and yeah, it's just one of the ways we check that things are working here. Of course, there's also a lot of unit tests in the and doc tests in the standard library. So you've probably seen the example code in all of these collections and stuff. So this code actually does, when you run x.py test, or even with just stage 1, or even with, I believe even stage 0 on libstandard will try to run these. It will actually build all of them and run them and check that they don't panic. Which of course, I mean, they are just normal Rust.doc tests, so that's kind of what you would expect. But we actually do this not just for the lib standard, but for the entire, but actually for all the compiler crates as well. They almost never contain tests like this, but they might contain unit tests, for example. And if you would add such a test, then it would also be run in the test suite. So we do actually have at least the ability to cover all kinds of stuff there. Yeah, like there's a lot of Rust C crates that, especially for like something like the data structures crate, yeah, there's a lot of stuff in here that doesn't really fit in libstandard or in liballoc, but we still want to test this properly, otherwise the compiler is going to have some weird and very hard to track down issues. So all of the tests in here do actually get run in during normal CI. So yeah. Okay. Okay, I think it's been almost 2 hours now. And yeah, I think I'm going to, unless there's any more questions, but I don't see any right now, going to end the stream soon. And yeah, thank you a lot for joining me. And maybe someone will actually use this advice I wrote down here to maybe make their first contribution to Rust, or even look into the more difficult parts of the compiler that might be slower than they could be, and maybe optimize performance there. Or yeah, and yeah, most important thing: never be afraid to ask someone. We do have plenty of chat rooms available for doing this sort of coordination before starting to implement something more complicated. For example, it's always useful to just check with people before starting some bigger project. Unless you just want to do it for fun and not actually land that. But yeah, generally, yeah, there's some pretty interesting tech in the compiler, which is why I'm contributing to it. Yeah, maybe someone else will, some of the viewers will make their first contribution soon. And yeah, thanks for joining me so far. I will post this somewhere, I think, just so that it doesn't get lost after the stream. Yeah, thanks for joining me, and goodbye.